Now, I wanted to explain to you about how to rotate certain poles from certain directions. Okay. Now, if we have these Ulfnets and stereopure projections, we can do the information. We can get the information about the rotation about an axis normal to the projection. What it means is I have stereopure projection in here, and if there are certain poles in here, P1, I wanted to rotate this pole, P1, from the normal lines to this stereopure projection. The normal lines to this stereopure projection is designated at the center. Okay, so from the center, this is 0, 0, 1 direction, for instance. This is the normal line, and there is certain pole in here in the stereopure projection, and I wanted to rotate this pole from these normal lines to certain angles. This information is the information that you cannot using Ulfnet. Ulfnet only shows the great circles and set of small circles, and in this case, this rotation should be done by using the small circles with the same radius with the P pole. Then you can measure the angles, and here, if you have 90 degrees, then this P1 pole should come here. And this information is not in the Ulfnet, so you have to do it by yourself. Okay, all right. But now what we'll do is the rotation about an axis lying in the plane of projection. What I mean in here is now I have certain poles in the stereopure projections P. Now I want to rotate this pole to certain directions which lies in the stereopure projection. Okay, for instance, 1, 0, 0 pole, 1, 0, 0 direction lies in the stereopure projection. Now I want to rotate it in here using this. This is as a rotation direction. Then what you do is you using the Ulfnet in here. Okay, you're using the Ulfnet in here, and you put this rotation axis to the north and south. Okay, then what you do is you have these great circles in here, and you have small circles in here, like this. Okay, you put your Ulfnet on top of this stereopure projection, and you put this rotation axis on the NX lines in here. Then there is a set of small circles. Then you can rotate. For instance, you can rotate A1 to this rotation axis of about 60 degrees. Then you can follow these small circles. Then this is 10 degrees, 20 degrees, 30, 40, 50, 60. Then if you rotate A1 axis to certain axis which lies in the plane, then this pole is now going to A2. For instance, if you have a B1 pole, rotate to this rotation axis by about 60 degrees, then you can rotate to the clockwise 10 degree, 20 degree, 30 degree, 40 degree. Now I have to rotate to 20 degree more. Then you go back these directions 20 degree. Now this is from upside to downside. Okay, I have the pole, I rotate it. Now it touches on the surface of this stereopure projection. You have to rotate to 20 degree more. Now the pole is not in the upper side, but is in the downside. And this downside pole is represented as minus in here. This upper pole is designated like this, but down pole can be designated like this. Okay, so you can rotate any directions which lies in the plane of the projection. In this case, rotating the axis to coincide with the NX axis, now moving the poles along their respective latitude circles, which is the part of the small circles. Okay. Now, it may not be clear, so let me draw one more drawings. This is like this. I have this stereogram like this. I have certain poles on here, P1, which is represented as in here, somewhere in here on the stereoscopic projection. Now I want to rotate it certain directions lying in the plane of projections. Then you rotate it. Then of course, if you rotate it further, then it will go down. This is north hemisphere, upper pole. Now it moves to the downside of this hemisphere, which is the south hemisphere. So now this is represented as the down pole instead of upper pole. Okay, I hope you understand what I try to deliver. Now, rotation about an axis inclined to the plane of projection. Now, your rotation axis is not on the vertical, not lies on the vertical, not lies in the plane, but it has certain angles. Okay. For instance, in this diagram, I wanted to rotate this A1 pole to this, which pole in here? Oh, B1 pole. B1 is the pole that I wanted to rotate, the direction of the poles, and I wanted to rotate this A1 pole to 40 degrees. Okay, this B1 pole, of course, is not in the plane of the projection, not on the vertical side of the projection. So what you do first is you put your stereoscopic projection and put this rotation axis, B1 pole, on the east and west side, like this. Then first, you make this inclined pole upside. Then you have to rotate certain degrees, which I meant is you put this B1 pole on the center of the stereoscopic projection, then you have to rotate your pole. Then in this case, you measure it, this 10, 20, 30, 40, 48 degrees. So you have to rotate your rotation axis to make it as a perpendicular to the stereoscopic projection. Then in this operation, this pole, which you want to rotate, also move to 48 degrees because you move your rotation axis. So this certain pole should also move by the same angles. And this moves on the small circles, then you go to 48 degrees on the part of the small circles, and now this one goes to A2. Now, in this case, the rotation axis is now vertical. So you can draw the angles of how much you rotate. Then this is the part of the small circle, which is not in the ULPNet, but you can draw the same radius circles. Then you can rotate about 40 degrees. This is what you want to rotate. Then this one coming to in here. Now, you have to go back your rotation axis to the original position. So you have to move this rotation axis, go back to original position, which is P3. Then, of course, this pole should also move the same angles through these small circles to 48 degrees. Okay? So if you rotate A1 pole by using this B1 pole as a rotation axis, and if you want to rotate to 40 degrees, then now finally this pole coming to A4. Okay? So again, now your rotation axis is not in the plane, not on the perpendicular. It has certain angles. So what you do is you put this rotation axis to the vertical lines. Then all this, the pole that you are interested in to rotate, they should move on the small circles by the same 48 degrees. Now your rotation axis is perpendicular, so now you rotate on the small circles. Okay, this information is not in the ULPNet, so you have to draw the radius, same radius circles, then you measure the rotation angles. Then you move back your rotation axis to the original position by using these ULPNets. Then, of course, this pole should move the same angles, and then this is the information that you can get. All right? So by using this stereoscopic projection and ULPNet, we can get the angles between two poles. And So we can get any information about how to rotate certain poles to certain directions, where this direction is either in the perpendicular to the stereoptic projection, or it can lies in the stereoptic projection. It can have certain angles, inclined angles, and then we can, using this Ulfness, to find out this where this the pole should move after the rotation operations. All right. Now, if you go to the crystallography textbooks, there are many standard projection information in here. It's about cubic. I explained some part of this in here. Let me just summarize about a few of the informations in here. Okay, this is 001 standard projection. So 001 pole, G-axis is the perpendicular to the sphere. Then this is 100 pole, this is 010 pole, 1 bar 00 pole, now 010 pole. Of course, in between 010, 100, if you rotate 45 degrees, you can measure this angle by using Ulfnet. Then there is a 110, so this is 45 degrees, and this is 45 degrees. Now there is a 111 pole in here. Okay, this 111 pole, 110 pole can be in a great circle by moving the Ulfnet. Then in the Ulfnet, you can measure the angle between these two poles and between these two poles. Okay. Now, let's say if there is a 001 pole in here, okay, then you can measure any directions which is in the 001 plane, where you can use all the directions in these lines, which is 90-degree separation from the normal lines. Then that's basically the zone axis, zone relationships, which means that all the directions in this line has 90-degree angle rotation, 90-degree angle separation from the 001 pole. If I have a 110 a pole in here, if I want to know any directions which is in the 111 plane, then what you do, you using the Ulfness and put the 111 pole on the east and west lines, then you can draw the set of great circles, which is 90-degree separation from this 111 pole. Then all the directions in these lines has basically 90-degree separation from 111. If I have 112 pole in here, again, by the same token, you can measure the 90-degree angle separation by using Ulfnet. Then you can draw the part of the great circles, and all the directions in here that has, again, 90-degree angle separation from 112 pole, means that this is the directions which lies on the 112 planes. All right, stereoptic projection in the textbook, there are a set of information about cubic 001 standard projections, and the cubic 111 standard projection. Okay, basically, if you have, let me go back, 001. Now, this is 001 standard projection, meaning that 001 is on the vertical direction on this stereoptic projection. Now, if I want to draw 111 standard projection of cubic, okay, so what you do is, from this previous slide, basically I wanted to move this 111 pole to these vertical lines. So this 111 pole should rotate this angle in these directions. Okay, then you can put your Ulfnet, part of the small circles in here. Then if there is any information that you are interested in, then should move the same angles from using these small circles. Then this 101 pole should move to here, because this pole, now you move, you rotate your 111 pole on a vertical lines. So any pole should move the same angles, should rotate the same angles. And you can do this operation by using Ulfnet by put these lines on the east and west and put all other planes on a part of the small circles, and you go the same angle rotations. Then basically you can draw this 1-1-1 standard projections, and again you can, by the same token, you can do 1-1-0 standard projections. Okay, I hope you do this operation by yourself and try to get the feelings of what I try to convey to you. Okay, I can explain to you, but unless you do it by yourself, you cannot really get the interesting features of these operations. But once you do it by yourself, you find it's quite interesting. Okay, it's amusing. All right, and I'll go to this 7 crystal system next time. But there is a hexagonal crystal structure. There is a standard projection of these hexagonal structures where the 001 plane locates on the vertical lines on these stereographic projections. And okay, so there are a few of the practice. What are the directions which lie on 1-1-1 plane? Okay, so there is a 1-1-1 pole in here. Okay, so I wanted to know the directions which lie on the 1-1-1 plane. Again, you put this 1-1-1 plane on the east and west. Then there is a small circles. There is a part of the small circles, looking like this. Then you draw 90-degree angle in here. Then there is set of lines you can draw, which is separated by 90 degrees. Then those are directions which lie on 1-1-1 plane. Then which 1-1-0 planes lie on 0-0-1 zone axis is the same thing. This is 0-0-1, then 0-0-1 zone axis, meaning that any directions which has 90-degree angle separation from this 0-0-1. So any 1-1-0 planes in these lines, okay, this is 1-1-0 planes, has again 90-degree angle separation from 0-0-1 zone axis. This is another 1 bar 1 0, and now this is 1 bar 1 bar 0. Okay, so there is 1 bar 0. This 4 1 1 0 type of planes has the 90-degree angle separation from 0-0-1 planes. So this is the practice that you can do. Okay, I explained to you about the stereogram and stereographic projections and how to utilize your openness to measure the angles between each poles and zone axis relationships, and how to rotate your poles to certain directions which either locates on the perpendicular to the stereographic projection and in the plane, and with any directions with certain angles. And well, you have to do it by yourself. I try to explain it to you as far as I can, but unless you do it by yourself, you cannot really get the interesting main point of these operations. So I strongly urge you to do it by yourself. Okay, thank you very much.